We started last time in section 5.1 with addition of integers, also did some with the absolute value, and we are moving on today into subtraction of integers. First definition, integer subtraction. If you have any integers a and b, to subtract a minus b will give you the unique integer n such that a is equal to b plus n. It's the definition of subtraction. And we have seen this before with whole numbers. We had an extra consideration when we did whole numbers that we actually had to have a bigger than b for that to work, and that a and b were whole numbers. But if you'll remember, basically the idea is that if you're taking a look at a minus b and it's going to be equal to some number n, the question is simply what would I have to add to the number b to get back to the number a. And that's how this is defined. So we define subtraction in terms of addition. One theorem before we look at some techniques for actually doing this. This theorem talks about how subtraction and adding negations or something like that, depending on your language, are the same. So if we have a minus b, that is the same thing as a plus a negative b. Okay? Okay, so what we're going to take a look at then is the same kinds of models we dealt with last time. Chip model, Chargefield model, number line model, and patterns model. Those were our four models, and we're going to do them now with subtraction. You guys ready? Yep. All right. So our first model, our chip model, remember we had this circle, and we had chips. What color were our chips that we did on my screen anyway? Do you remember? Black and red. So there were black chips that were, what's the deal about black chips? Positive. They're positive chips. And then we had, like you said, red chips. And the red chips were negative chips, and we talked about the fact that if you use anything different color-wise or filling something in or something like that, you're going to give me a key just so that I can make sure I understand your work. All right, so on this one, this says I need to have 5 positive chips, right? That's where it starts. So we're going to start out by drawing 5 positive chips. Okay, now let's actually read what this says. What does this sign right here mean? Take away or remove. Okay, so this is a take away. We're going to take something away. But what does it say I'm supposed to be taking it away? 3 what? Negative chips. So that's 3 red chips in this model, right? And I've got a problem. We don't have any red chips to take away. Everybody agree? So somehow I have to get some red chips in here so that I can remove them. I've got to put something in so that I can take it back out. So here's how I do that. I put in a red chip. But of course you can't just put in a red chip. That makes the value something different than it was before. So if I put in a red chip, what do you think I have to do to balance what I just did? I have to put in a black. I mean, see, I don't want to take out the red. I mean, the whole goal is to get 3 reds in here. So if I put in a red, I have to put in a black. Is everything in that circle still equal to the number 5? Yeah, it's weird looking 5, but it's 5. It's okay. Because I have 6 positives and 1 negative, right? Okay, it's like borrowing $1 from somebody that you already have the dollar at home for. Something like that, right? Okay, but I need 3 reds. So I don't want to just put 1 red in my circle. I want to put 3 reds in my circle. But what do I have to do to balance the 3 reds I put in my circle? I have to have the 3 blacks that go with them. So these 3 red chips need to be in there. So we get to insert them in there. But we have to insert them in what are called 0 pairs. Okay, so a 0 pair is a pair of 2 things that equals 0. A red and a black chip together equals 0. So I can put them into my circle as long as I put them in together. Okay, this circle still equals 5, right? But now it has 3 red chips that I can remove. So that's what we're going to do next. We're going to take these 3 red chips and we are going to remove them. That's the taking out or the subtracting of the 3. And then I can take a look at what I have left. So what do I have left? I have 8 black chips. And this picture, and you may not like this one, but this does give justification for why in the world subtracting a negative is addition. I subtracted a negative 3 and I ended up with adding the 3, right? Because I put them in 0 pairs. So this is the answer, 8.
So in algebra,
Mm-hmm.
we would normally just make that a plus
Make what a, oh, yes. Yes, so again, remember these models that we're doing are like the first thing you would teach a child in learning why something works. They're not the thing that you're going to do every single time you see one of these questions. So yes, this would actually give justification for why it is, when you were talking about, that this is actually equal to 5 plus 3. Yes. And we'll give a couple more with justification for this exact same model, because this is where students get a little bit confused. And I think I might have even told you guys, I had a, actually it's a friend, we'll just call her a friend, and she homeschools. She has a 13, 14-year-old daughter, and her daughter told her, she was really struggling to try to get her daughter to understand why these two negatives give you a positive like this. Negative times negative is a positive. And her daughter just got so frustrated, she decided it was blasphemy. Yes, it's blasphemy. So there you go. All right, oops, I didn't mean to do that. All right, so we're going to do the same thing now, but we're going to do it with a charged fields model. We talked last time about the fact that charged fields models are very, very similar. So the 5 at the beginning tells me, what do I have in my circle? 5 positives. And then, of course, the subtraction sign means I need to take something away. What do I need to take away? I need to take away 3 negatives, but I don't have 3 negatives, right? So how do I get there to be 3 negatives? 0 pairs. So I put them in one at a time, right? There's a 0, here's a 0, and here's a 0. Now there are 3 negatives that can be removed, and my resulting circle has 8 positives. Okay. Now we're about to do something a little bit different, because this is the number line model. I mentioned this in passing, really, yesterday or 2 days ago, I guess, in class. We're going to start at 0 and we're going to go over 5. Okay, so our first move is to go over 5. And obviously we're going to move over 3 more to end up at 8. But I want to justify for you as I walk across the classroom why this works. Okay? So again, your kinesthetic learners is great. Here's what you do. So you're facing positive direction, right? So this line is positive, behind me is negative. This is positive. So I'm going to move 8. Or sorry, 5. I've got 1, 2, 3, 4, 5. Okay? The negative tells me that I'm going to turn around. Okay? That's the takeaway negative. Tells me I'm going to turn around. And then the other negative 3 tells me I'm going to walk backward 3. Here's 1, 2, 3. So one of the negatives tells me turn around. Write this down because you can't draw it very well. The total effect is lost when you try to draw this out. But you turn around, and then the second negative tells you walk backwards. Now when you turn around and you walk backwards, you end up walking in the positive direction, right? That's what's happening. And so we can do it physically really well. We just can't draw it very well at all. Make sense? Okay. So that one's a really nice one to move around with. And then the pattern model. So we did patterns last time. Told you again, not every model appeals to every child. But for those who are mathematically minded, at least this gives justification for why this makes sense. Again, our goal is to justify why negative times negative is a positive, which is basically what we're doing in this example. So here, we're going to start out with something we know. Whole numbers. 5 minus 2 is 3. 5 minus 1 is 4. Sorry. 5 minus 0 is 5. Okay, so that's just whole numbers, right? All the stuff we've done before. And then we get into the integer part with the negative. So now we have 5 minus negative 1. In a moment, we're going to have 5 minus negative 2. And then our final result, which is where we're headed, is the 5 minus negative 3. Now, what we're doing is we're going to repeat the pattern that's happening on the left. So it started from 3, 4, 5. So what comes next? 6, 7, and 8. So simply by looking at the pattern of what's happening, we can also justify that 5 minus a negative 3 must be 8, because the pattern has to continue with the process. It's good? Okay. One more item that is a little bit, I don't know why they've thrown a few of these things in here in this particular point in time. We did absolute values in our last little examples. Now we're going to look at PEMDAS. So have you guys seen PEMDAS before? This is order of operations, tells you the order in which to do things, right? So let's remind ourselves what each, well, first of all, before I do that, what's the like sentence that you've heard? Fabulous. Please excuse my dear Aunt Sally. Has everybody heard that before? A couple of you haven't. That's okay. Some people remember it just by PEMDAS, the word itself. Some people remember it by that acrostic is what it's called. So here's what we have going on. The P, do you remember what the P stands for? It's not really for please. What does it really stand for? Somebody said parentheses. This is parentheses. What does the E stand for? Exponents. Okay, now M and D usually occur in that order, but there's really nothing special about the ordering of M and then D. We could have just as easily done D and then M, okay? Sometimes people are like, really? The answer is yes, really. So M, of course, is for multiplication, and D is for division. So this is multiply, divide. So if it doesn't matter if we multiply first or divide first, then how do we decide? Well, we move from left to right. If the multiplication occurs first, we do it first. If the division occurs first, we do it first. Okay, this is all about left to right. And the same is true for the addition subtraction on the next one. We move from left to right. So this is addition and then subtraction, left to right. One thing I would like to make you aware of that sometimes people get confused about is up here where you do parentheses. I didn't realize that was so thick. Let me try it a little bit thinner. Parentheses. This means what happens inside. So it doesn't mean get rid of parentheses. It means simplify what's inside of them if that can be simplified. And sometimes it can and sometimes it can't. So it doesn't mean that you're supposed to do anything with the parentheses per se except for simplify what's inside of them. Any questions on this? This always seems like a very basic thing, but I always have students miss quite a few questions when it comes down to actually processing through these. So be very careful. Make sure that you really are moving left to right, that you're really doing the things in the order that you're supposed to do them in. Now, here is a question. It says to simplify with the order of operations. So one of the questions that you're going to have is going to change the directions a little bit, and it's going to say something like this. What is the last thing you have to do? Okay, well, which means you have to do the whole process, and then you have to say what the last thing is that you have to do. The reason that they ask it in that way is because we recognize fully that you guys have fancy calculators that can do all of this for you. And it understands order of operations, right? When you're working with kids who are learning about order of operations, they aren't using fancy calculators, and we don't really want you or them to actually rely on the fancy calculator to do it. So that's why they're asking the question that way. So let's do this problem together, and then we'll answer that same question of what was the last thing I did. So when you're looking at this problem, what operation are we actually going to do first on this one? The division is going to be first, right? It's either multiplication or division, and the division comes first. So we'll take it really slow, like one step at a time exactly. And we're going to do a 3 here, right? 6 divided by 2 is 3. What would I do next? The multiplication. And then I would do subtraction. This is why I did this problem, is because I did all of them backwards of what you're used to doing, comfortable with doing, right? Subtract before I add. So 5 minus 2 is 3. And I realize that you could do the 3 and the 12. You could do all that in the same step. But this is actually the question that your book ends up asking. What's the last thing you do? Well, the last thing you do on this problem is actually add 3 plus 12. Does that make sense? Okay, so, and then of course my answer here on this problem, the way that I've worded it, is 15. But that's how your questions are going to be asked when you see at least one of the questions that you're going to see that people tend to misunderstand when they get there. Any questions on this one? All righty.